In the beginning, there is only a cloud, a vast and seemingly endless swirl of gas and dust suspended in the quiet void of interstellar space. Gravity, the most patient of sculptors, begins its invisible work. Over millions of years, the particles drift closer together, colliding softly, joining, compacting. Slowly, the cloud becomes denser at its heart, and as more matter falls inward, the pressure rises. What was once a faint mist in the darkness becomes a glowing sphere. A star is born, and with its birth comes light. From that moment, the life of a star is a balance between two opposing forces. Gravity forever pulls inward, demanding collapse, while nuclear fusion pushes outward, creating a radiant pressure that holds the star's weight at bay. This dance of destruction and creation defines the shining existence of every star. The sun itself lives by this fragile peace, burning steadily as hydrogen fuses into helium in its core. For billions of years, this stalemate continues, but the story is different for the Titans. The stars, many times more massive than the Sunday. Their lives are shorter, fiercer, and their endings unimaginably violent. A massive star consumes its fuel with reckless speed, where a modest star like the Sun will last for more than 10 billion years. A star 10 or 20 times its mass may burn through its life in only a few million years. The immense pressure in its core means hydrogen vanishes swiftly, fused into helium. Helium, in turn, fuses into carbon, then oxygen, then neon, magnesium, silicon. Each successive stage grows shorter, until the final steps occur in only days. Deep inside, the core becomes a factory of heavy elements, forging the building blocks that will one day seed new worlds and living beings. Yet this relentless progression leads to an inevitable wall: iron. Iron is a dead end for fusion. Lighter elements release energy when fused. Heavier ones absorb it. Once a core becomes iron-rich, the delicate balance shatters. Gravity gains the upper hand, and collapse begins. Imagine an object larger than Jupiter, its fiery body weighing many times the mass of the Sun, suddenly losing the pressure that supported it. In a fraction of a second, its heart falls inward. The collapse accelerates to speeds that defy comprehension. Atoms are crushed, electrons are forced into protons, creating neutrons and a flood of nearly massless neutrinos. The core shrinks to the size of a city before it halts. This sudden stop sends a shock wave rippling outward through the star's falling layers. The star detonates as a supernova, an explosion so bright it can outshine an entire galaxy for weeks. For a moment, the death of a single star can rival the combined light of billions. The energy released in that instant is more than the Sun will emit in its entire 10 billion year life. And within that cataclysm, heavier elements like gold and uranium are forged and thrown across the cosmos, scattered into the clouds that will one day birth new solar systems. When you hold a piece of gold in your hand, you hold the ashes of a long-dead star. Yet while the outer layers are blown away into space, the collapsed core remains. It is here that the most astonishing transformation takes place. The remnant, composed almost entirely of neutrons packed together like an unimaginable crystalline sea, resists further collapse. Neutron degeneracy pressure holds gravity in check, halting the implosion. What is left behind is a neutron star, one of the densest forms of matter in the universe, the last stop before becoming a black hole. Picture the Sun, the vast sphere that holds nearly the entire mass of our solar system. Now imagine compressing all of that into a ball only 20 kilometers across. That is a neutron star, a city-sized object with a mass greater than the Sunday. Its surface gravity is hundreds of billions of times stronger than Earth's. Its density is beyond human intuition. A single teaspoon of its matter would weigh more than a mountain. The very laws of physics bend under its conditions, and reality itself feels strained. The neutron star is a monument to collapse, a place where nature pushes matter to its limits. It is a star that has died, yet in its death, it reveals the extremes of what matter can become. Each neutron star is a reminder that gravity is the ultimate artist, capable not only of shaping galaxies but of squeezing the very fabric of matter into something almost unrecognizable. But this is only the beginning of the story. We can describe the collapse, we can measure the light of the explosion, but what does it truly mean to speak of density so great that mountains vanish into spoonfuls? To answer that, we must leave behind the violence of the supernova and step into the quiet mystery of measurement itself. We must ask what density really means and why a neutron star takes the concept to its furthest extreme. And so the story flows onward from the roaring death of stars to the simple yet profound question of how much matter can be packed into a given space. It is here that the teaspoon of a neutron star will reveal itself as more than a fact. It will become a key to understanding the most extreme physics in existence. The neutron star sits silent in the darkness, its birth a memory of unimaginable violence, yet its presence is proof that gravity does not relent. To truly grasp what has been created, we must picture the life that came before, the fiery furnace that held balance for millions of years. For those millions of years, hydrogen atoms slammed together at the core, fusing to form helium and releasing light. The outward push of this light held back the crushing weight of the star's mass. But in the moment iron filled the core, the outward push died, and the collapse began. That collapse was unstoppable, like a mountain breaking free and rushing down a slope, gaining speed with every heartbeat until it slams into the valley floor. In less than the time it takes for a human to blink, the heart of the star fell inward, shrinking from a sphere thousands of kilometers wide to just a few dozen. Neutrinos, born from the violent conversion of particles, streamed outward by the trillions upon trillions, carrying away energy and marking the death cry of the star. For the briefest of moments, nearly all the energy of the explosion was held within these ghostly messengers, streaming into the cosmos, unseen by almost everything, yet forming a storm of particles that would pass through whole planets as though they were nothing but fog. The outer layers of the star, freed from their moorings, met the rebounding shockwave and erupted outward into space. The star had lived for millions of years, yet in a moment, less than a second, its fate was decided. Its corpse, the neutron star, stood as a monument to collapse. When one imagines a neutron star, the mind strains to comprehend it. Consider the sun itself, whose mass makes up nearly all the matter in the solar system. The sun is 1,400,000 kilometers across, its volume so vast that over 1 million Earths could fit inside. Yet if you could compress all that mass into a neutron star, it would shrink until it was no wider than a city, barely 20 kilometers across. The thought staggers the imagination. A star that once blazed across light years now sits like a tiny ember, yet heavier than almost anything the universe can create. The density of such an object is beyond words. If one were to take a cube of neutron star material, only a few centimeters across, it would weigh more than Mount Everest. A teaspoon of that same matter, if somehow removed and placed upon the Earth, would weigh billions of tons, enough to crush mountains flat and burrow deep into the planet. But this is a thought experiment, for in truth no such piece could survive outside the crushing embrace of the star's gravity. The very act of removing it would unravel its structure, the neutrons spreading apart like prisoners freed from confinement, releasing energy so fierce it would devastate anything nearby. Yet in its natural environment, held in place by gravity that defies imagination, neutron star matter remains stable. The surface of the star is a crust of exotic nuclei and degenerate matter, beneath which lies a sea of neutrons packed so tightly that individual atoms no longer exist. Beneath that crust, the density rises still further, perhaps into realms of matter we cannot yet define, perhaps even into seas of quarks, the particles that make up neutrons themselves. Each neutron star is both a relic and a mystery, a laboratory written into the sky where physics is pushed beyond the reach of our machines. The conditions at its surface are no less terrifying. The gravity is hundreds of billions of times stronger than Earth's. A human who somehow found themselves upon that surface would be crushed instantly, their body reduced to a layer thinner than paper in a fraction of a second. To lift even a feather from that surface would require the strength of billions of tons. Escape velocity there is not a few kilometers per second, as it is on Earth, but nearly half the speed of light. Light itself, though free to escape, bends and twists under the immense gravity, warping the appearance of the star and making it seem larger than its island. And yet, neutron stars are not silent. Some spin hundreds of times per second, emitting beams of radiation that sweep across space, like cosmic lighthouses. These pulsars, as they are called, are some of the most accurate clocks in existence. Their rotations steady enough to rival atomic timekeepers on Earth. The very act of their emission is made possible by the density of their bodies, their magnetic fields, their mass and spin bound together in an intricate dance that turns death into signal. All of this, the crushing collapse, the unimaginable density, the relentless gravity, stems from one truth: stars die. They are not eternal. Their brilliance is finite. And for the massive ones, the end is spectacular. To understand a neutron star is to look at the moment when creation meets destruction, when the balance of gravity and fusion shatters and the universe reveals what lies on the far side of collapse. And this brings us closer to the question at the heart of this story. How do we make sense of density when density surpasses all human experience? How do we compare a teaspoon of neutron star matter to the mountains and oceans and cities we know? In the next step of this journey, we must pause and ask what density truly is and why the concept bends under the weight of neutron stars. Only then can we begin to comprehend what it means for a spoonful of matter to weigh more than a mountain. The neutron star rests at the heart of the supernova remnant, surrounded by expanding clouds of gas and dust glowing in the light of radioactive decay. For a time, it may be hidden, obscured by the very matter ejected during its creation. But slowly, as the debris spreads thinner across space, the remnant reveals itself. What was once a brilliant star lighting entire systems is now a small, dense point whose properties are stranger than anything we encounter on Earth. To understand it, let us follow the collapse one final time in thought. Picture an immense ball of gas, millions of kilometers across, its outer layers falling inward with unimaginable speed. In the instant of collapse, atoms themselves are torn apart. Electrons are crushed into protons, forming neutrons. The core becomes a single ocean of neutrons bound together, not by chemical forces, but by the quantum rules that refuse to let particles overlap completely. It is this resistance, called neutron degeneracy, that halts the collapse before it can fall further into a black hole. And yet, it is a balance achieved at the very edge of possibility. Should the original star have been just a little more massive, no pressure would have been able to resist gravity's pull, and the core would have plunged beyond the point of return. A black hole would have formed, trapping light itself within its grasp. Neutron stars therefore exist as narrow survivors, perched between survival and annihilation, proof that the universe draws fine lines between what can and cannot exist. Seen from afar, they are deceptively modest. A neutron star, only 20 kilometers across, emits no steady blaze like the stars we see in the night sky. Its light is faint compared to the burning giants it once resembled. Yet what it lacks in outward size, it more than makes up for in inward extremes. Its magnetic field can be trillions of times stronger than Earth's, bending space around it into whirling funnels of charged particles. Its rotation can be so rapid that it completes hundreds of spins in a single second, each turn sending beams of radiation sweeping across the galaxy, like the hands of a clock too perfect to falter. These pulses were once a mystery, detected by radio telescopes as repeating signals so regular that astronomers briefly wondered if they might be messages from another intelligence. But they are no more artificial than the sunrise. They are the heartbeat of neutron stars, the rhythm of collapse turned into signal. Each pulse that reaches us is a reminder of the violent birth of the star and of the unimaginable forces compressed into its core. To stand near such an object, if it were possible, would be to face gravity so immense that no structure could survive. A mountain would collapse into a thin layer across its surface in an instant. The human body would be torn apart before thought could even register the experience. The atmosphere of the star is only a few centimeters thick, a fragile boundary between the vacuum of space and the ocean of neutrons beneath. And yet, out of such extremes comes knowledge. By observing neutron stars, by measuring their pulses and spectra, scientists uncover truths about matter at densities never achieved on Earth. These cosmic remnants are not merely strange curiosities. They are laboratories written into the fabric of the universe. They show us how far the rules of physics can be stretched, and in doing so, they help us test our own understanding of reality itself. The collapse of a star is not just the death of light, but the creation of something far more alien. It is the compression of billions of years of fusion into a single, enduring remnant. It is the revelation that density can exceed imagination. To comprehend a neutron star is to confront scales of mass, pressure, and gravity that stretch human language to breaking. And still, we try. We describe mountains shrinking into teaspoons. We speak of suns packed into cities. We reach for metaphors because the reality is beyond the human mind's instinctive grasp. This is where the journey must pause. For before we can explore the teaspoon of neutron star matter itself, we must understand density in its most familiar forms. What does it mean to measure mass against volume, to compare water to iron, Earth to white dwarfs, and stars to neutron stars? Only by grounding ourselves in this language can we take the next step into the true weight of wonder. The story of collapse has brought us here, to the threshold of comprehension. The next step is to strip away the fire and the violence and to ask a simple question. What is density? And why does it define the fate of stars? When we speak of density, we are trying to measure something deceptively simple. It is the amount of mass contained in a certain space. Take a cube, fill it with a substance, and then weigh it. Divide the weight by the size of the cube, and you have its density. The concept is so familiar that we often overlook how profound it. Island density tells us why wood floats while stone sinks, why planets form layers with heavy metals at the core and lighter gases above, why stars shine or collapse. It is not just a number on a chart. It is the story of how matter arranges itself under the rules of physics. Imagine holding a stone in your hand. It feels heavy compared to its size. Now hold a piece of wood, the same size. It feels lighter. This difference is density, and your hand instinctively measures it every time you pick something up. Earth's oceans, Earth's mountains, Earth's very shape are all determined by density. It is the quiet law that governs everything from the smallest pebble to the largest star. On Earth, densities vary across a modest range. Water, the reference we often use, has a density of 1 gram per cubic centimeter. Ice is slightly less dense, which is why it floats. Wood, depending on the type, might be half as dense as water, or nearly equal to it. Rocks are heavier, with granite and basalt, reaching around 3 grams per cubic centimeter. Metals go further. Iron, one of the heaviest common materials, reaches almost 8 grams per cubic centimeter. Lead is even higher. And in the laboratories of Earth, we can manipulate substances into strange forms, but rarely do we escape densities much greater than a handful of grams per cubic centimeter. Now imagine compressing the entire Earth into the density of water. The planet would swell to a size far larger, becoming a giant pale sphere floating through space. If instead we compressed Earth into the density of iron, its radius would shrink. Earth as it is today rests at about 5.5 grams per cubic centimeter, pulled into that state by the weight of its own gravity. Gravity squeezes Earth just enough to keep its iron core heavy and dense, surrounded by lighter rock and ocean. In this balance, our planet finds its shape and stability. But what happens when density is pushed further than Earth can manage? For this, we must look to the stars. A white dwarf, the corpse of a sun-like star, is supported by the pressure of electrons themselves, their refusal to be packed too closely together. Its density is staggering compared to anything on Earth, rising to millions of grams per cubic centimeter. Imagine a teaspoon of white dwarf matter. It would weigh as much as a car. This is already beyond ordinary imagination, and yet it is only the beginning of the story. A neutron star, the remnant of a supernova, takes this concept to the brink of possibility. Instead of being held up by electrons, it is crushed further, until the very protons and electrons fuse into neutrons. The density leaps not by a factor of 2 or 3, but by orders of magnitude. A teaspoon of neutron star matter weighs billions of tons. Billions. The difference between water and neutron star matter is like the difference between a feather and a mountain. How can we compare such extremes? One way is to think of volume. The human body has a density close to water, so our average density is about 1 gram per cubic centimeter. Iron is about 8 times denser than that. A white dwarf is millions of times denser than iron. A neutron star is billions of times denser still. To say the words is one thing, to grasp them is another. If Earth were compressed into neutron star density, it would shrink from 12,000 kilometers across to no larger than a small town. Density is the hidden thread weaving through the universe. It decides whether a cloud of gas becomes a star or drifts silently in the void. It decides whether a star lives for trillions of years or dies in a few million. It decides whether the end is a quiet ember, a white dwarf cooling slowly into blackness, or a neutron star blazing with impossible density, or a black hole erasing itself from sight entirely. Density is destiny. And so we must ask ourselves, if the density of neutron stars is so far beyond what we know, how do we even begin to imagine what a spoonful of such matter would weigh? The answer is not easy, for no ordinary comparison will suffice. We must stretch thought itself, reaching for images that can carry the weight of billions of tons packed into something so small you could balance it on your fingertip. Only then can we take the next step toward understanding the famous teaspoon of neutron star matter. The human mind is quick to compare, yet comparisons fail when numbers swell beyond ordinary scale. When we speak of density on Earth, the range is comforting. Water as 1, wood as less than 1, iron as nearly 8, lead as about 11. These are numbers that feel tangible because we encounter them every day. A ship floats because its overall density is less than water. A stone sinks because it is denser than water. We are accustomed to this intuitive order. But the moment we step beyond Earth, the familiar ground vanishes beneath us. Consider Earth itself again. Its density is about 5.5 times that of water, and it holds this value because of compression. Gravity squeezes the inner core until iron and nickel are packed far tighter than they would be in a laboratory sample. Pressure rises as one descends, climbing through layers until it reaches the outer and inner core, where atoms themselves deform under stress. And yet, even at its heart, Earth is still an island of low density compared to the corpses of stars. White dwarfs, the quiet embers left after stars like the sun shed their outer layers, defy this intuition. They are small, no larger than Earth itself, yet their mass is comparable to the Sunday. How can something so small weigh so much? The answer is electron degeneracy. In such stars, electrons resist being compressed into the same state, and this resistance halts collapse. A single cubic centimeter of white dwarf material weighs tons. Tons in a cube no bigger than a sugar cube. And yet, this is only the first step toward the extreme. The leap from white dwarfs to neutron stars is like walking from a hilltop into a canyon whose depths stretch beyond vision. Where a white dwarf packs matter until atoms lose their structure, a neutron star packs it further, until protons and electrons vanish into neutrons. The space between particles collapses. Matter becomes a sea of neutrons flowing like a fluid, each one pressed against its neighbor. This is density no longer measured in grams per cubic centimeter, but in billions upon billions. To compare, let us imagine volumes once more. A liter of water weighs 1 kilogram. A liter of iron weighs about 8 kilograms. A liter of white dwarf matter would weigh millions of kilograms. A liter of neutron star matter would weigh hundreds of trillions of kilograms. It is no longer meaningful to think of lifting it, for nothing on Earth could contain such mass. Even the crust of the planet would collapse beneath it, sinking to the core as if it were falling into the center of gravity itself. And yet, density is not an abstract monster. It is a principle we can measure and describe. It is the same equation we use to find why ice floats or why helium balloons rise. Density equals mass divided by volume. The only difference is scale. At one end of the spectrum lies air, with its molecules spread thin. At the other end lies neutron star matter, where no space remains between particles at all. When we speak of neutron stars as the densest objects short of black holes, it is because black holes are not defined by density in the usual sense. A black hole hides its mass behind an event horizon, a boundary where light itself cannot escape. The density inside is undefined, perhaps infinite, but a neutron star is visible, tangible, measurable. We can weigh it by watching how it bends the motion of nearby stars. We can time its pulses. We can sense its gravity. It exists at the knife edge between physics we can see and physics we cannot yet fathom. All of this brings us back to the teaspoon, a small measure, familiar to every kitchen, now turned into the stage for the universe's most extreme comparison. If a teaspoon of neutron star matter were somehow transported to Earth, it would weigh billions of tons. This single fact captures in one sentence the unimaginable density we have been chasing. But before we confront that scenario directly, we must linger on the idea itself. For to say it is one thing, to imagine it, to feel the scale of it, requires us to pause and stretch the limits of our thought. The density of neutron stars is not merely a curiosity. It is the essence of what remains after collapse, the mark of how far matter can be pressed without breaking entirely. It is the universe's way of saying this is the limit. Here is where atoms cease to exist as we know them. Beyond this point lies the abyss of black holes. And so, to grasp a teaspoon of neutron star matter is to glimpse the final frontier of density itself. The stage is set. We have followed density from water to rock to metal, from planet to white dwarf, from white dwarf to neutron star. Each step has multiplied weight beyond reason. Now we are ready to hold, in imagination at least, that tiny spoon filled with the densest substance in the cosmos. And it is here, in this thought experiment, that we will discover just how crushingly heavy the universe can become. The teaspoon rests in imagination, an ordinary tool for stirring tea or measuring sugar, now transformed into the vessel of an impossible truth. In that small hollow of metal we place not grains of salt or drops of liquid, but the collapsed matter of a dead star. At first, the scale seems absurd. How can a spoon, a symbol of the ordinary, be asked to carry billions of tons? And yet, this is what density has brought us to. It is not the spoon that changes, it is the matter itself, packed until the space between particles vanishes, until a universe of weight is compressed into something the size of your hand. The power of this image lies in its simplicity. We cannot easily picture a city-sized object containing more mass than the sun, but we can picture a spoon resting on a table. We know what a spoon feels like when it carries a few drops of water. We know how easily we lift it. And now we are told that if it were filled with neutron star matter, it would weigh more than a mountain, more than every building, every ship, every car on Earth combined. The mind recoils, for the scale is too vast. And yet the numbers are real, drawn from the simple truth of density, multiplied to the extreme. To sense this, let us step back through the ladder of densities once more. A teaspoon of water weighs only a few grams. A teaspoon of iron weighs nearly 50 grams. A teaspoon of white dwarf matter weighs many tons. enough to crush a car. A teaspoon of neutron star matter weighs billions of tons, equal to a mountain, equal to the total weight of humanity, equal to forces beyond all human machinery. This is no exaggeration. It is the plain arithmetic of density carried into the realm of stars. But how do we feel it? To say a number is not enough. Numbers slide past the ear without leaving weight. We must imagine. Picture standing at the base of Mount Everest, looking upward, at its peak, lost in clouds. Now, imagine lifting that mountain with a spoon. Picture every human being on Earth, billions of us together, standing in one place. Now imagine lifting all of humanity in a spoon. This is the weight of neutron star matter, and it is only a teaspoon. It is not surprising that comparisons strain here. Language itself bends under the pressure of such numbers. When physicists speak of neutron stars, they know that metaphors are needed to convey what equations alone cannot. To describe them as dense is true but empty. To describe them as mountains in spoons, as suns in cities, as gravity beyond all endurance, is to make the impossible visible. And yet, behind the metaphor lies a truth deeper than wonder. The density of a neutron star is not an accident. It is the outcome of collapse, the natural result of stars greater than the sun exhausting their fuel. It is the threshold just before gravity wins completely, just before matter falls into the blackness of a black hole. A neutron star is the last stop on the road of physics we can still see. To hold its density in a spoon is to touch the boundary of the possible. The question now arises, if such matter is so dense, if it cannot survive outside its native gravity, then what would truly happen if a spoonful were brought to Earth? Could it rest on a table? Could it sit in the palm of a hand? The answer is both astonishing and terrifying. Freed from the crushing gravity of the neutron star, the matter would expand, explode, and release more energy than the largest weapons humanity has ever built. It could vaporize a city in an instant. The teaspoon is a thought experiment, and it must remain so, for the reality would be catastrophic. This is why density must always be spoken of in context. Neutron star matter exists only within neutron stars. Outside of them, it dissolves back into ordinary particles, releasing energy that would shake the Earth. The spoon is a window into possibility, not an invitation to reality. Yet even as a metaphor, it holds power. It reminds us that the universe can compress mountains into teaspoons, that gravity can sculpt suns into cities, that density itself can stretch imagination to its breaking point. And so, as we close the door on this chapter, we carry forward a new vision of density. No longer is it just a measure of grams per cubic centimeter. It is a story of collapse, of stars that burn bright and die young, of remnants that defy all human intuition. It is a measure that leads us from wood to iron, from Earth to white dwarfs, from white dwarfs to neutron stars. And beyond neutron stars lies the black hole, the final abyss, where even density refuses definition. But before we cross that frontier, we must linger on the teaspoon itself, for in its impossible weight lies the most famous fact about neutron stars, the one comparison that captures the attention of scientists and dreamers alike. The idea begins simply. A spoon is something so ordinary that every person on Earth knows it well. It is the measure of a small portion, a tool found in every kitchen, a symbol of the everyday. And yet, when scientists seek to explain the unimaginable density of a neutron star, they turn to this small, familiar object. They say, if you could scoop up just a teaspoon of neutron star matter, it would weigh billions of tons. In that single image lies the full strangeness of collapsed matter. It is an image so powerful that it has become the most famous fact about neutron stars, repeated in classrooms, books, and documentaries. A spoonful that outweighs mountains. A spoonful that equals all of humanity. A spoonful that captures the essence of physics pushed to its ultimate edge. The staggering weight comes from the collapse that formed the star in the first place. Inside the heart of a massive star, Gravity overcame the push of fusion, and the core imploded, until neutrons were pressed side by side, with no space left between. The matter that once made up atoms is now bound so tightly that the empty space we take for granted is gone. Ordinary matter is mostly empty space, with nuclei surrounded by distant clouds of electrons. In a neutron star, that space has been erased. What remains is mass, raw and unyielding, packed into a volume so small that the human mind rebels at the thought. Imagine lifting a teaspoon of water. It is so light that we barely register it in our hand. Imagine lifting a teaspoon of iron filings. It is heavier, but still familiar. Imagine lifting a teaspoon of gold. It is heavy, but manageable. Now try to imagine lifting a teaspoon of neutron star matter. The weight would be so crushing that no table could support it, no building could withstand it, no planet could endure it. The ground beneath your feet would give way, the mass sinking toward the center of Earth, tearing through rock and mantle as if they were air. The teaspoon is no longer a kitchen tool, it is an icon of impossibility. This is why scientists reach for it as a metaphor. To say billions of tons is one thing, but to tie it to a spoon, to an object held daily in human hands, is to make the fact unforgettable. The comparison anchors the abstract to the real. It shows how the extraordinary hides inside the ordinary, how a humble spoon can reveal the most extreme truth of the cosmos. It is not exaggeration. The math has been checked and rechecked. Density, multiplied by volume, leads inevitably to the figure. A spoonful of neutron star matter outweighs mountains and continents. To understand the scale, imagine Mount Everest. Its mass is measured in billions of tons. Place that mountain upon one side of a scale, and on the other side, place a teaspoon of neutron star matter. The spoon would sink the balance. Imagine gathering all of humanity, every man, woman, and child, and weighing their combined mass. Again, the teaspoon would outweigh them. In fact, a single spoonful could exceed the combined weight of every human-built structure on Earth, from skyscrapers to ships to airplanes. The comparison is so extreme that it borders on the surreal, yet it is not fiction. It is the natural consequence of physics at work. The power of this fact lies also in what it says about the limits of matter. We think of mass as tied to size, yet the teaspoon shows that volume is deceiving. What matters is density. The universe can compress mountains into spoonfuls, and it can compress suns into cities. A teaspoon of neutron star matter is more than a number. It is a challenge to our senses, a reminder that the reality of the cosmos is stranger than the imagination of myth. And so, the teaspoon becomes the entry point into the mystery of neutron stars. It is a fact so startling that it captures even those who have never studied science. It is the hook that pulls the mind into deeper questions. How can matter be so dense? How can neutrons be pressed so close? What forces hold them together? What would happen if such matter touched Earth? Each of these questions flows naturally from the spoon, and each reveals another layer of the story. The teaspoon fact is more than trivia. It is a bridge between human experience and cosmic scale. It invites us to look at something small and see within it the weight of the universe. It invites us to imagine the unimaginable, and it shows that science, at its best, does not only explain, it astonishes. The teaspoon becomes a stage for thought experiments that stretch the imagination to its breaking point. Let us place it upon a table here on Earth. At once, the table collapses. The floor caves in. The ground yields. The teaspoon does not sit. It sinks, drawn by its own weight, as if Earth itself were made of soft wax. It would burrow through soil and stone with unstoppable momentum, carving a tunnel toward the core. The crust, mantle, even the iron heart of Earth would offer no resistance. For against billions of tons in so small a volume, all matter behaves like air. Now imagine placing it upon a scale. The pointer would not move. It would shatter. No machine, built by human hands, could withstand the pressure. To measure the weight of such a sample would require instruments the size of planets, and even then, the act would destroy them. The truth is that the teaspoon cannot exist on Earth at all. Outside the gravity of the neutron star, the forces that hold neutrons together relax. In fractions of a second, the matter would expand violently, releasing energy so great that cities would vanish in fire. The teaspoon, the simplest of metaphors, becomes in reality a weapon beyond imagination. Yet the thought experiment persists, because it is not about bringing neutron star matter here, but about understanding what density means there. On the surface of the neutron star, the spoonful is ordinary. It sits as part of a crust kilometers thick, resting atop the neutron ocean beneath. It does not explode. It does not tear through rock, because it is contained by gravity billions of times stronger than Earth's. There it is stable, here it is impossible. This contrast is what makes the spoon such a powerful image. It is a reminder that context is everything, that density depends on the environment, that matter itself changes its nature when pressed by gravity beyond comprehension. And so we return to comparisons. If a teaspoon of neutron star matter weighs as much as Mount Everest, then imagine what an entire cup would weigh, or a barrel, or a swimming pool. Each step multiplies weight until the comparisons collapse under their own absurdity. We could say a cupful would outweigh continents, that a barrel would outweigh the oceans, that a swimming pool would outweigh the moon. The words are true, but the imagination fails, for the scale is too vast. And so we return again and again to the teaspoon, because it is enough. It is the smallest measure that still contains infinity. The spoon also teaches humility. It reminds us that our world, so vast to us, is fragile against the forces of the cosmos. The mountains we climb, the cities we build, the oceans we cross, all are light compared to what a single spoonful of collapsed matter contains. It is not to belittle Earth, but to place it in perspective. The universe holds scales that dwarf us, and yet here we are, able to imagine them, to measure them, to speak of them with awe. The teaspoon is the bridge between the human and the cosmic, between what we hold in our hands and what lies in the stars. And as the thought experiment ends, we are left with a truth that lingers. The famous fact is not trivia. It is a distillation of collapse, of density, of gravity, of the final fate of massive stars. To say that a teaspoon of neutron star matter weighs billions of tons is to tell the story of how stars die and what remains after their fire is gone. It is to remind us that the universe is more extreme, more dramatic, more astonishing than any myth, and it leads us onward toward deeper questions. If matter can be crushed so far, what becomes of the atoms themselves? What happens when the structure of matter dissolves into something beyond our knowledge? The teaspoon has shown us the weight. Now we must explore the cost. The spoon glimmers in thought, balanced between the ordinary and the impossible. We have weighed it against mountains, against continents, against the sum of all human bodies, and still, its measure staggers the mind. But to stop here would leave the story unfinished, for the true wonder lies not only in the weight, but in the reason behind it. Why does this spoon hold such crushing density? Why do neutrons, the quiet building blocks of matter, carry within them the power to outweigh worlds when pressed together? To answer, we must look beneath the surface, into the structure of matter itself. Ordinary matter is mostly empty space. Atoms, the units of chemistry and life, are made of tiny nuclei, surrounded by vast clouds of electrons. The nucleus itself is only a fraction of the atom's size, while the electrons dance at distances thousands of times greater. Imagine a cathedral with a single grain of rice at its center. That grain is the nucleus, and the soaring arches above it are the empty electron cloud. This emptiness is why matter seems soft, why it can be cut, shaped, compressed. The solidity we feel is not from particles touching, but from electrical repulsion, the refusal of electrons to share the same space. Inside a neutron star, gravity overwhelms this repulsion. The cathedral collapses, The grain of rice expands to fill the hall. Electrons are driven into protons, forming neutrons, and the empty space vanishes. Atoms, as we know them, no longer exist. What remains is a sea of neutrons crammed side by side, held together by the strong nuclear force, the most powerful bond in nature. The spoonful owes its weight to this transformation, to the stripping away of emptiness until only mass remains. This is why the spoon is so heavy. It is not filled with atoms in the way our world is, but with particles that have been pressed past every barrier. Each neutron is nearly identical, each one packed so tightly that no further compression is possible without breaking matter apart entirely. A spoonful of such substance is not merely dense, it is final. It is matter at its end, at the point where physics itself says no further. Beyond this, collapse must continue, and a black hole is born. Yet even here, on the edge of impossibility, the spoon reveals beauty. It shows us that the familiar can hold the extraordinary. A kitchen tool becomes a vessel for cosmic truth. A simple measure becomes the symbol of extremes. Through it, we glimpse how the universe recycles its stars, how death can create remnants more astonishing than life, how density itself shapes the fate of matter. And so the famous fact, repeated in classrooms and whispered in wonder, is more than a curiosity. It is the clearest way we have to describe a neutron star's nature. A teaspoon weighs billions of tons. A teaspoon holds the mass of mountains. A teaspoon bridges the human and the cosmic. It is a fact that endures, because it is not only true, but unforgettable. The spoon now passes us forward. We have seen its weight. We have traced the path from empty atoms to solid neutrons. We have felt the collapse that gives it meaning. But still, a question remains. What does it mean to strip atoms bare, to crush them until they cease to exist? How can electrons vanish, protons merge, and matter transform into a single ocean of neutrons? To follow the teaspoon further is to enter the heart of collapse itself, to watch as atoms are destroyed and a new kind of matter is born. Atoms are the foundation of everything we see, touch, and breathe. They form the air, the water, the rocks, and our very bodies. Each atom is a tiny universe of its own, with a dense nucleus at the center and a swarm of electrons moving in the vast space around it. Most of the volume of an atom is empty, a void compared to the speck of matter it contains. This is why ordinary matter feels the way it does. It is why you can walk through air, why you can bend metal with enough force, why you can crush coal into diamond. Matter yields because most of it is space. But what happens when space itself is taken away? What happens when atoms are squeezed until their structure collapses? This is the story written into neutron stars, the story of crushing atoms into something entirely new. The first barrier against collapse is electron degeneracy. Electrons obey a rule of quantum mechanics called the Pauli exclusion principle, which states that no two identical particles can occupy the same state at the same time. Imagine a crowded theater where every seat must be filled by only one person. When all the lower seats are taken, newcomers must climb higher, filling balconies and galleries, piling upward in energy rather than position. This pressure, though invisible, is real. It is what supports white dwarfs, the remnants of stars like the Sunday. Their matter is so compressed that electrons form a rigid sea, creating a pressure that halts collapse. But electron degeneracy has limits. When a star is too massive, gravity pushes beyond those limits. The electrons cannot hold. Under the crushing weight, electrons are forced into protons, combining to form neutrons and releasing a torrent of neutrinos. In an instant, the architecture of atoms dissolves. Nuclei merge, electrons vanish, and the world of chemistry ends. What remains is a sea of neutrons packed shoulder to shoulder, a fluid of particles so dense that space itself seems erased. This is neutron degeneracy, the second and stronger barrier against collapse, and it is what creates neutron stars. To imagine this is to strip matter of its identity. Think of a carbon atom. the backbone of life. 6 protons, 6 neutrons, 6 electrons. It forms bonds, creates molecules, builds proteins, and DNA. Now imagine crushing it. The electrons vanish into the protons merge with neutrons, and all the chemistry that made life possible is gone. A carbon atom becomes nothing but neutrons, indistinguishable from any other. Multiply this by the uncountable atoms of a star, and you have a neutron star, an object that is no longer made of atoms at all, but of a single, continuous substance. The teaspoon of neutron star matter owes its weight to this transformation. Atoms contain vast empty space, but neutrons crammed together contain almost none. A mountain of empty space becomes a spoonful of solid matter. It is not that mass has increased, but that volume has collapsed. Density leaps by factors of billions, and the ordinary rules of matter vanish. To hold such a spoonful would be to hold the end of atoms themselves. And yet, even this is not the ultimate limit. If the star is heavier still, neutron degeneracy will fail. Gravity will force collapse past neutrons, past all resistance, into a black hole where matter vanishes behind an event horizon. Neutron stars exist on the razor's edge, the last stable form of matter before physics surrenders to gravity's abyss. Crushing atoms is more than destruction. It is a transformation into something new. It reveals that matter can take forms we never see on Earth, that the familiar world of elements and molecules is not the final word. In the depths of neutron stars, the universe shows us that atoms are fragile, that their beauty is fleeting, and that under pressure, they give way to a deeper order. To understand this is to see why the teaspoon weighs so much, and to glimpse the strange horizon where matter itself ceases to be. The crushing of atoms is a story told not in sudden explosions but in relentless pressure, the steady and irresistible weight of gravity that will not yield. In the heart of a massive star, when the last fusion flames sputter out, the core becomes a trap with no escape. Gravity presses inward with such force that the very structure of matter is undone. Atoms, which once defined the chemistry of life and the solidity of matter, are stripped bare. Their electrons, the guardians of distance, are driven into the protons they once orbited, creating neutrons in a flood of particle reactions. The building blocks of the periodic table, the elements of the cosmos, dissolve into something featureless and alien. In this sea of neutrons, individuality vanishes. There are no carbon atoms, no iron atoms, no gold atoms. There are only neutrons pressed together, shoulder against shoulder, locked by the strong nuclear force and confined by gravity. The result is a fluid so dense that the idea of emptiness no longer applies. The neutron soup is not like liquid water, nor like molten rock. It is not like anything we can touch or see on Earth. It is a phase of matter that exists only in these cosmic furnaces, created by conditions no laboratory can replicate. The stability of this neutron ocean is granted by neutron degeneracy pressure, the quantum rule that forbids neutrons from sharing the same state. Just as electrons once held back collapse in white dwarfs, neutrons now take their turn. They resist being pressed into the same energy level, and in doing so, they push back against gravity. For a time, this resistance is enough. The star halts its collapse and stabilizes, frozen in a form no larger than a city, yet weighing more than the Sunday. The balance is precarious, and it exists only because the star's mass is within a narrow range. Too little, and it would have stopped as a white dwarf. Too much, and even the neutrons could not resist, and the core would plunge into a black hole. Neutron stars are the survivors, perched on the thin ridge between what is stable and what is annihilated. Their very existence is a cosmic coincidence, a reminder that physics finds limits, not in theory, but in reality. To picture the neutron soup, imagine the empty space of atoms erased. On Earth, the nucleus of an atom is tiny compared to the electron cloud, with nearly all the atom being void. In a neutron star, that void is gone. Particles sit so tightly together that they form a solid continuum. A cubic centimeter of this matter, no larger than a sugar cube, would weigh more than a mountain. A teaspoon would outweigh continents. And yet, within the star, it is simply matter, pressed flat and held in equilibrium, like the surface of a sea, too immense to comprehend. This sea may hide even deeper mysteries. Some physicists believe that under even greater pressure, neutrons themselves may break apart, dissolving into quarks, the fundamental particles that compose them. If so, then within the heart of a neutron star lies not only neutron soup, but perhaps quark soup, an even stranger state of matter where the distinctions between particles blur. Whether this exists remains uncertain, for no telescope can peer into the core, but the possibility lingers, a reminder that the universe may hold states of matter more exotic than we can imagine. The crushing of atoms is therefore not an end but a transformation, a doorway into new forms of existence. It tells us that matter is not fixed, that what we see around us is only one chapter in a longer story. Atoms gave rise to chemistry. Chemistry gave rise to life. But under the weight of stars, even atoms yield. They dissolve into neutrons, and in doing so, they reveal the universe's ability to reinvent itself. And all of this, the collapse of atoms, the rise of neutron degeneracy, the possibility of quark matter, is contained within that single image of a spoon. The weight is more than a number. It is the symbol of matter without space, of particles pressed until individuality dissolves. The teaspoon is not merely heavy, it is the marker of atoms destroyed, of matter transformed into a sea that cannot exist anywhere else. This is the secret behind the teaspoon's impossible weight. It is not a trick of numbers or a curiosity of physics. It is the direct consequence of crushing atoms into neutrons and neutrons into soup. It is the universe showing us how far matter can go before it collapses into invisibility. And in this crushing, we see not only destruction, but the creation of something new, something so extreme that it bends the very definition of matter. Ordinary matter is fragile compared to the forces at play inside a neutron star. The elements we know, the molecules that form air and water and life, are held together by delicate bonds between electrons and nuclei. These bonds give us the world we recognize. They allow crystals to form, metals to bend, gases to flow. But if any of this matter were lowered onto the surface of a neutron star, it would not remain intact for even the blink of an eye. The immense gravity and pressure would strip it bare, erasing the structure of atoms as completely as a flame erases mist. Picture a rock falling toward a neutron star. From a distance, it looks solid, its atoms arranged in a lattice, its bonds strong enough to withstand great pressure. Yet, as it approaches, the tidal forces stretch it, tearing it apart, long before it reaches the surface. The closer it falls, the more intense the forces become. By the time it nears the star, the rock is no longer a rock. It has been shredded into dust, then into atoms, then into particles. The electrons are ripped from their orbits, forced into protons, collapsing into neutrons. The rock is consumed, dissolved into the neutron soup, and its identity is gone. The same would be true for anything we know. A mountain lowered toward the star would vanish into neutrons. A human body would be torn apart layer by layer, until nothing remained but particles joining the endless sea. Even a spacecraft built of the strongest materials would fail instantly, its atoms unmade, as if they had never existed. In the environment of a neutron star, the very rules of matter are rewritten, and nothing ordinary can endure. The crust of the neutron star itself is an alien landscape. It is thought to be a thin, rigid shell, only a kilometer thick, made of nuclei packed in ways that cannot occur on Earth. Beneath it lies the neutron ocean, dense and featureless, pressing outward with unimaginable pressure. Even this crust is unstable, cracking and shifting under stresses so great that the releases can send bursts of radiation across space. These starquakes, as they are called, are like the shattering of continents, but on a scale that shakes the cosmos. This contrast between ordinary matter and neutron matter highlights why the teaspoon image is so powerful. It is not just about weight, it is about the impossibility of survival. A spoonful of neutron matter cannot be scooped and carried away like liquid. It cannot be stored, studied, or touched. Freed from the neutron star's gravity, it would expand violently, its neutrons no longer forced together. The teaspoon would unravel, exploding into a storm of particles and energy that would devastate everything nearby. The fact itself is a metaphor, a way of grasping the ungraspable, a bridge between the familiar spoon and the alien reality of collapsed matter. Yet even as we acknowledge this impossibility, the thought experiment remains useful. By imagining the teaspoon, we capture the scale of density, the crushing of atoms, the transformation of matter. We remind ourselves that the universe contains states of being far beyond our senses, states that can only be described through comparisons that strain our imagination. The teaspoon is not real, but the density it represents island. This is the lesson of crushing atoms. It shows us that the familiar world is only a fragile arrangement of space and particles, that under enough gravity, even the strongest bonds vanish. It shows us that matter can be pressed into new forms, alien and extreme, existing only under the weight of dying stars. And it prepares us for the next step in our journey. For if a spoonful of neutron star matter is so impossibly heavy, what would truly happen if we could bring it to Earth? Could it sit upon a table? Could it rest in our hands? Or would it tear the world apart? The teaspoon waits again in imagination, and this time we lift it from the surface of the neutron star and carry it home. What would happen if we place that fragment of collapsed matter on Earth? At first, the idea seems simple, like bringing back a sample of rock from the moon. But neutron star matter is not rock. It is not even matter as we know it. It is atoms crushed until their structure is gone. Neutrons locked in a sea that exists only under the crushing grip of gravity billions of times stronger than Earth's. Remove it from that gravity, and the illusion shatters. The neutrons, freed from their confinement, would no longer hold together. They would decay into protons, electrons, and neutrinos. In that moment, the teaspoon would not remain still. It would explode, unraveling into a storm of radiation and particles. The energy released would dwarf the most powerful weapons humanity has ever built. A city would vanish in a flash. Stone, steel, and air would be vaporized in the blink of an eye. The teaspoon is not merely heavy, it is catastrophically unstable outside of its home. This is why the metaphor must remain a thought experiment. We cannot scoop neutron matter and carry it across the gulf of space. The moment it leaves the embrace of neutron star gravity, it ceases to exist in the form we imagine. But in imagination, we may still ask, suppose we could place it intact upon the Earth's surface. Its weight alone would be enough to tear through crust and mantle, burrowing toward the core. It would not stop, for nothing could support it. It would sink until it reached the very center, dragging Earth into chaos. As it tunneled downward, the planet would quake, oceans would rise, mountains would collapse, all in answer to the teaspoon's impossible weight. Yet this thought itself reveals something important. The density of neutron star matter has meaning only where it belongs, within the neutron star itself. There, gravity balances pressure, and the sea of neutrons is stable. Here, on Earth, the balance is gone. The teaspoon shows us the extreme, but it also shows us that context is everything. Density is not absolute. It is tied to the environment that sustains it. What exists safely in the core of a dead star becomes impossible anywhere else. Still, the question lingers, because humans cannot resist asking what if? What if such a sample was somehow protected, locked in a field that prevented it from expanding? What if it could be studied? The answer is that the knowledge would be priceless. It would reveal the secrets of matter under pressures we cannot recreate. It would tell us whether neutrons remain intact or dissolve into quarks, whether strange particles emerge, whether new states of matter exist beyond our theories. But this is fantasy. The reality is that neutron star matter cannot be bottled, cannot be carried, cannot be placed in a spoon upon a table. It belongs to the stars, and it can only be observed from afar. And yet, even knowing this, the image has power. It reminds us of the scale of physics, of the gulf between our world and the extremes of the cosmos. It shows us why neutron stars must be studied as they are, by watching their pulses, their emissions, their gravitational effects. It shows us why the teaspoon is not a sample but a symbol, not an object but an idea. It shows us the limits of imagination and the necessity of humility. So if you brought it to Earth, it would not rest in a spoon. It would explode in violence. It would sink to the core. It would destroy the ground beneath our feet. The thought experiment collapses into catastrophe. But in that collapse lies the truth. The teaspoon of neutron star matter belongs only where gravity is strongest, where atoms are crushed, where stars have died. It is a measure not of what we can hold, but of what we can imagine. To imagine the catastrophe in fuller detail, let us carry the thought further. Suppose the teaspoon of neutron star matter were placed gently upon the surface of Earth, as though it were nothing more than a sample of soil or a fragment of meteorite. Instantly, the balance would fail. The neutrons, no longer confined by the crushing gravity of their native star, would fly apart. In fractions of a second, they would decay into protons and electrons, releasing neutrinos that would pass through the planet as if through smoke. The decay itself would release a storm of radiation, flooding the air with lethal energy. The teaspoon would not remain still. It would expand, unravel, and detonate with power equal to nuclear arsenals many times over. Cities would vanish in an instant, vaporized in white heat. The shockwave would sweep outward faster than sound could carry it, flattening everything in its path. Stone would turn to vapor. Steel would flow like liquid. Oceans would boil. In a moment of release, the teaspoon would become a weapon beyond imagining. Its energy, more than any human technology could hope to control. This is the first truth of bringing neutron matter to Earth. It cannot exist here, and the attempt to force it would mean destruction. Yet even if the neutrons did not decay, even if some magic held them together, the teaspoon would still spell disaster. Its mass alone, billions of tons compressed into a volume no larger than your finger, would pull upon the planet with unstoppable force. It would sink into the ground, dragging soil, stone, and water into its wake. The crust would fracture, earthquakes would ripple across continents, volcanoes would erupt as pressure was forced through faults and fractures. The teaspoon would burrow relentlessly toward the core, pulled not only by Earth's gravity, but by its own. The planet would reel under its weight, and balance would shatter. As it fell, the teaspoon would not shrink, but would carry its mass unchanged. The further it sank, the more heat it would release, turning rock into magma, carving a path of fire. In time, it would rest at the center, altering Earth's gravity itself, tugging oceans into new shapes, shifting the balance of the planet's rotation. Life would not survive such an addition. The teaspoon would not merely rest, it would consume the world with its presence. But of course, the teaspoon cannot be brought here. It is bound to its home by the same laws that make it possible. Remove it, and it unravels. Release it, and it explodes. Imagine again that teaspoon resting in a spoon on your table, appearing calm, a silent fragment of a dead star. You could look upon it for less than a breath before it tore itself apart, reducing everything around you to ash. The image is haunting because it contrasts the familiar with the impossible. The ordinary utensil of daily life becomes the vessel of cosmic catastrophe. This is why the teaspoon fact endures, not only because of its weight, but because of its impossibility. It teaches us that the universe holds states of matter that cannot leave their context. It teaches us that density is not merely about numbers, but about the environments that sustain it. It teaches us that Earth, safe and stable to us, is fragile against the extremes of the cosmos. The teaspoon is a reminder that reality is local, that what exists under one gravity cannot exist under another. And yet the fascination remains. Scientists dream of somehow studying such matter, of capturing even the faintest hint of its properties. Experiments in particle accelerators try to mimic the pressures of collapsed stars, colliding atomic nuclei at near the speed of light to create fleeting droplets of dense matter. These droplets live for only instants, but in those instants they reveal hints of what lies inside neutron stars. It is the closest we can come, the faintest echo of the teaspoon. Thus, the question of bringing neutron matter to Earth is answered. It cannot be carried, cannot be held, cannot be studied in a laboratory. It exists only within neutron stars, under the crushing pressure of gravity itself. The teaspoon lives only in imagination, and in imagination, it shows us both the wonder and the danger of cosmic density. The teaspoon waits in thought, heavy with meanings it cannot carry into our world. We have imagined its arrival upon the surface of Earth, and we have seen how quickly it would unravel, how violently it would release its energy, how ruthlessly it would sink into the planet's core. But the truth remains simple. Neutron star matter belongs only where it was born. It can exist only within the crushing weight of a dead star's gravity. Outside of that gravity, it is impossible. The teaspoon is not a souvenir to be carried home. It is a metaphor, a bridge for imagination, a window into density that lies beyond experience. This truth tells us something deeper about the universe. Matter is not the same everywhere. It changes with pressure, with temperature, with gravity. On Earth, water flows as a liquid, but in the icy moons of Jupiter, it may freeze into crystalline forms, never seen in our oceans. In the atmospheres of giant planets, hydrogen may compress into metallic states that shine and conduct like copper wire. And in neutron stars, matter crosses its final threshold, collapsing into neutrons pressed so tightly together that space itself is erased. Each environment shapes matter into something new, and the neutron star is the ultimate example of this transformation. So when we say that a teaspoon of neutron star matter would weigh billions of tons, we must remember the condition hidden within the fact. That weight is real only where gravity is strong enough to hold it together. Without that gravity, the matter dissolves, decays, or detonates. The teaspoon's weight is meaningful only in its home. It is not something we can import to Earth. It is something we must imagine from afar. Standing on our small and fragile world, gazing into the night sky where such stars reside. This realization brings a kind of humility. It reminds us that we cannot control or capture every part of nature. There are realms of matter and energy that belong only to the cosmos itself. We can measure them, we can calculate them, we can imagine them, but we cannot touch them. And perhaps that is as it should be. For to hold a teaspoon of neutron star matter would be to hold destruction itself, the compressed heart of a sun, the last cry of a star's collapse. And so the thought experiment closes. The teaspoon is not here. It remains in its place, locked within the gravity of a neutron star, a measure of density too great to be borrowed. But its lesson travels with us. It shows us that weight is relative, that density is contextual, that matter becomes what gravity commands. The teaspoon belongs not to Earth, but to the stars. This prepares us for the next step. If the teaspoon is impossible here, if its weight has meaning only under neutron star gravity, then we must turn our attention to that gravity itself. What does it mean to stand on the surface of a neutron star? What would a human weigh there? What would it take to escape its pull? The answer lies not in spoons or mountains, but in gravity multiplied to billions of times Earth's strength. A force so intense that light itself bends under its sway. To understand the teaspoon fully, we must now walk across the surface of a neutron star and feel its gravity pressing down. To understand the weight of neutron star matter, we must now place ourselves upon its surface, a place where gravity is no longer a gentle pull, but a crushing command. On Earth, we live under a gravity that feels absolute. But in truth, it is modest. A stone falls when dropped, a person stands upon the ground with ease, and an athlete can leap into the air for a brief moment of defiance. The escape velocity of Earth is 11 kilometers per second, a speed far beyond human muscle, yet well within the reach of rockets. We think of this as powerful because it defines the limits of our world, but compared to the gravity of a neutron star, it is almost nothing. On the surface of a neutron star, gravity is hundreds of billions of times stronger than Earth's. The comparison is so extreme that it bends language. Imagine standing there for even an instant. The moment your feet touch the ground, you would be crushed into a layer thinner than a sheet of paper. Bones and organs would collapse into a smear of particles, not because of impact, but because of weight. On Earth, your body weighs perhaps 70 kilograms. On a neutron star, that same body would weigh billions of tons. Each heartbeat would carry the weight of mountains. Every cell would be pressed flat in less than a fraction of a second. The crushing force is not limited to humans. Imagine placing a feather on the surface of a neutron star. On Earth, it drifts gently to the ground, its weight almost invisible. On the neutron star, that feather would strike the surface with the energy of a bomb. For gravity there accelerates everything with unstoppable speed. The smallest pebble becomes a weapon, the lightest particle, a hammer. Nothing can touch the surface gently. Every meeting is violent, and yet, the neutron star remains intact, held in perfect balance between the inward pull of gravity and the outward push of neutron degeneracy pressure. Its crust, only a kilometer thick, withstands these forces, though it cracks and quakes under the strain. When it does, bursts of energy are released into space, signals that travel across light years. These starquakes remind us that even the most stable objects of collapse are still restless, their surfaces trembling under gravity's demand. Escape from this surface is nearly impossible. On Earth, 11 kilometers per second will carry you away from gravity's pull. On the Moon, a mere 2 kilometers per second is enough. But on a neutron star, the escape velocity is nearly half the speed of light. A rocket would need to accelerate, not to thousands of kilometers per hour, but to hundreds of millions. No material could withstand the forces. No engine could generate the thrust. No pilot could survive the acceleration. Once you fall upon a neutron star, there is no leaving. It is gravity's final embrace. The curvature of space around such a star is equally dramatic. Light itself bends as it passes near, warping the image of the star so that more than half its surface can be seen at once. To an observer, it appears swollen, distorted, larger than its island. The horizon of the neutron star is not flat, but curved by gravity's hand. It is a vision that seems dreamlike, yet it is measured in the equations of general relativity and confirmed in the signals we detect from pulsars. Standing on Earth, we take gravity for granted. We climb stairs, we drop stones, we watch tides rise and fall. But on a neutron star, gravity is a force that redefines meaning itself. It is not simply a pull, it is the sculptor of matter, the destroyer of atoms, the prison of light. And to imagine standing there, even for a second, is to confront the fact that no human body, no machine, no structure could endure. The surface gravity is the ultimate reminder that the teaspoon's weight is not fiction. It is reality, written into the very shape of collapsed stars. To linger upon the surface of a neutron star in imagination is to witness gravity in its most absolute form. Consider the ordinary objects of daily life: a cup, a coin, a grain of sand. On Earth, each has a weight that seems small, barely noticed in the hand. On a neutron star, each becomes a colossal burden. A coin would weigh as much as a skyscraper. A cup would press downward with the force of a mountain range. A grain of sand would strike the crust with the violence of an asteroid impact. Gravity does not allow gentleness there. Every object is a projectile. Every step, an act of destruction. This crushing force does not only act upon matter, it acts upon light itself. General relativity tells us that mass bends space-time, and the greater the mass, the greater the curvature. Around Earth, the bending is subtle, detectable only with precise instruments. Around a neutron star, it is dramatic. Light leaving the surface loses energy. Climbing out of the star's gravity well, it shifts to red, its wavelength stretched by the effort. To a distant observer, the star's light appears dimmer, its signals slowed. Time itself seems to pass differently, slower near the surface than far away. Clocks would tick at different speeds, not because of gears or springs, but because space-time itself is warped. Imagine holding a clock in your hand on the surface of a neutron star. To you, it ticks normally, each second following the last. But to someone watching from afar, the clock slows, its seconds stretching into long intervals. This is not illusion, but reality. Time runs differently under gravity's rule. The surface of the neutron star becomes not only a place of crushing weight, but a place where the very flow of time is altered. The escape velocity, nearly half the speed of light, defines the scale of this gravity. Rockets on Earth must reach only 11 kilometers per second, a speed within the reach of human technology. To escape a neutron star, a rocket must achieve more than 100,000 kilometers per second. It is not simply a matter of stronger engines. It is a matter of impossibility. No material could survive the stresses. No passenger could endure the acceleration. No fuel could provide the energy. The surface is a prison, and once captured, nothing can leave except light itself, and even that light leaves wounded, bent, and redshifted. The consequences of such gravity extend outward. Space around the neutron star is distorted, curved like a lens. Stars behind it may appear shifted, their light bent around the star's mass. The star itself looks swollen, larger than it should be, because light from its far side curves around to meet our eyes. The result is a place where vision itself is unreliable, where what you see is not what exists, where space and time have been sculpted by gravity into strange new forms. And yet, within this prison of gravity, order remains. The neutron star spins, sometimes hundreds of times each second. Its magnetic field whirls, accelerating particles to near the speed of light. Radiation beams outward in precise rhythms, sweeping across space like the hands of a perfect clock. The very density that creates the crushing surface gravity also creates stability, allowing these remnants of collapse to endure for millions of years. The star does not fall further. It does not dissolve. It remains as a balance point between destruction and endurance, an object where gravity is supreme, but not absolute. To imagine standing there is to confront impossibility. No suit could protect you, no ship could support you, no technology could resist the weight. And yet, through imagination, we can glimpse what it means to exist under such conditions. We can see how density, gravity, and time weave together into a fabric unlike anything on Earth. The surface gravity of a neutron star is not just a number. It is the ultimate test of matter, of light, of time itself. It is the environment in which the teaspoon of matter gains its true meaning, where billions of tons packed into a spoon are not impossible, but ordinary. The imagination trembles as it lingers on the surface of a neutron star. We have seen how a feather becomes a weapon, how a grain of sand carries the violence of an asteroid, how light itself bends and time slows. Now let us carry these comparisons further, for the scale of gravity here deserves its full measure. On Earth, the weight of your body is familiar, a comfort that defines the way you walk, the way you rise from a chair, the way you fall asleep. On a neutron star, that weight multiplies by hundreds of billions. A body weighing 70 kilograms becomes billions of tons. The simple act of standing becomes impossible, the very concept of movement absurd. You are flattened into the crust before thought can take shape. Consider a human heartbeat. On Earth, It is the gentle rhythm of blood, a soft pulse of life. On a neutron star, each beat would try to pump blood against a weight billions of times greater. The heart would collapse into silence in less than a fraction of a second. Even the strongest materials we know, diamond, graphene, the engineered alloys of spacecraft, would fail instantly. No bond, no structure, no design could resist. This is gravity not as we know it, but gravity in its purest, fiercest form. And yet, astonishingly, it is not the final word. Beyond the neutron star lies the black hole, where escape velocity surpasses even the speed of light, where nothing, not even photons, can leave. The neutron star is the last visible threshold before that abyss. Its surface gravity, crushing beyond comprehension, is still a surface, still a place where matter resists collapse. It is the ultimate laboratory of density that remains within reach of observation. We can see it, we can measure it, we can time its pulses and study its signals. The black hole gives us no such privilege. This comparison deepens our understanding of the teaspoon. The impossible weight of that tiny measure makes sense only when tied to the surface gravity of its home. Billions of tons in a spoon are meaningful because gravity holds the neutrons together, because degeneracy pressure still resists collapse, because the star remains intact. On Earth, the spoon would explode. On a neutron star, it simply rests, indistinguishable from the rest of the crust. Weight itself has meaning only within context, and the neutron star shows us how gravity defines what is possible. The surface gravity also explains why these objects endure for millions of years, slowly cooling but never dispersing. Their matter is locked in place by pressure too immense to yield. Their radiation and magnetism are driven by the spin of their dense cores, stabilized by gravity's relentless pull. In their pulses and their signals, we hear the echo of collapse, the rhythm of a surface so heavy that even imagination struggles to hold it. And so, as we step back from this crushing landscape, we prepare to see neutron stars not only as objects of density and gravity, but as cosmic beacons. Their rotation, their magnetic fields, their light sweeping across space, turn them into pulsars, lighthouses of the universe. The teaspoon taught us density, the surface taught us gravity, and now the pulses will teach us time. In the next stage of this journey, we will watch how neutron stars spin, how they shine, and how their impossible stability turns collapse into signal. When a neutron star is born, it does not rest in silence. It spins. It spins because the collapsing core of a star conserves its angular momentum, the same way a figure skater spins faster when drawing in her arms. A star once millions of kilometers across shrinks to only 20 kilometers, and in that shrinkage, its rotation accelerates to dizzying speed. Some neutron stars spin only a few times per second. Others spin hundreds of times per second, so fast that their crusts are stretched by centrifugal force, yet held intact by gravity, billions of times stronger than Earth's. These cosmic remnants become lighthouses in the sky, sweeping their beams across the universe with precision so perfect that they rival our best atomic clocks. The beams come from their magnetic fields, which are among the most powerful in nature. A neutron star's magnetic field can be trillions of times stronger than Earth's. As the star spins, its field whirls with it, accelerating particles near the surface to nearly the speed of light. These particles stream outward, releasing radiation in narrow beams. If Earth happens to lie in the path of such a beam, we see a pulse of light every time the star rotates. This is why we call them pulsars. They are neutron stars that sweep their beams across the cosmos like silent beacons, flashing with every turn. At first, when these signals were discovered, they seemed so regular, so precise, that astronomers wondered if they might be artificial. The pulses came like the ticking of a clock, exact and unchanging, repeating with such order that no natural phenomenon on Earth could compare. But further study revealed their true source. They were the voices of neutron stars, the echoes of collapse, the rhythms of gravity and density, turned into light. What seemed at first to be a message was in truth a natural signal. Yet, it remains no less astonishing for being so. Imagine watching one of these pulsars. The star itself is small, invisible to the naked eye, hidden in the darkness of space. Yet its pulse arrives across thousands of light years, a flicker of radio waves or X-rays that reaches our telescopes with unwavering precision. Each flash tells us the star has turned once more. Each flash is a heartbeat of matter compressed to its limits. Some pulsars have been pulsing for millions of years, their rotations slowing only slightly with time. They are clocks written into the fabric of the cosmos, and their accuracy surpasses even the instruments of human engineering. This precision allows pulsars to serve as tools of discovery. By measuring their pulses, astronomers have detected planets orbiting distant stars, weighed the mass of neutron stars, and even tested the laws of relativity. The steady ticking of pulsars provides a yardstick across light years, a signal against which we can measure the universe itself. In their constancy, we find guidance. In their regularity, we find proof of physics at scales otherwise beyond our reach. And yet, behind the science lies a deeper wonder. These pulsars are not simply beacons. They are reminders that collapse is not the end of a star's story. Even after fusion has ceased, even after supernova has shattered the outer layers, the remnant continues to speak. It speaks not in light that shines steadily, but in pulses that sweep across the sky, rhythmic, unerring, eternal, on human timescales. The death of a star becomes a signal. The silence of collapse becomes a beacon. When we imagine a teaspoon of neutron star matter, we think of weight, of density, of destruction. But when we imagine pulsars, we see something different. We see creation within destruction, order within collapse, light within darkness. The same density that makes the teaspoon weigh billions of tons makes the pulsar a perfect clock. The same gravity that crushes atoms into neutrons holds the star's spin steady for millions of years. The teaspoon and the pulsar are two sides of the same truth. The beams sweep across space, unrelenting, reaching worlds that will never know their source. They are cosmic lighthouses, guiding us not with intent, but with inevitability. And through them, the neutron star reveals itself not only as an object of density, but as an object of signal, an instrument of measurement, a beacon of wonder. The pulses continue, sweeping through the cosmos like the steady rhythm of a metronome, and with each turn they remind us of the order hidden within collapse. A neutron star, born in violence, becomes a timepiece of extraordinary precision. To grasp this, consider again the speed of their rotation. Some pulsars complete a rotation every second, others dozens of times per second, and the fastest known whirl hundreds of times each second. Imagine a star the size of a city spinning faster than the blades of a kitchen blender, its crust stretched to the breaking point, its magnetic fields tearing through space. And yet, despite this violence, the timing remains steady, the pulses arriving with accuracy greater than the most delicate mechanisms built by human hands. This precision makes pulsars cosmic clocks. Their pulses can be measured to fractions of a millionth of a second. Over years and decades, they remain consistent, drifting only slightly as the star loses energy to radiation. Some pulsars have been observed for half a century, their timing so steady that astronomers can predict their next pulse with astonishing accuracy. These stellar clocks are not subject to rust or wear. They are not slowed by friction or gears. They are driven by the inertia of collapsed matter and the laws of physics themselves. The power of these clocks extends beyond wonder. They provide tools for measuring the universe. When a pulsar orbits another star, the slight variations in its pulse timing reveal the presence of its companion. This is how astronomers discovered the first planets beyond our solar system, not through telescopes that captured their light, but through pulsars that betrayed their tug. By listening to the pulses, astronomers detected the rhythm of orbiting worlds, alien planets invisible to the eye, but revealed by the ticking of a dead star. Binary pulsars tell an even deeper story. When two neutron stars orbit each other, their gravity sends ripples through space-time itself. Waves predicted by Einstein's theory of general relativity. These gravitational waves carry away energy, slowly drawing the stars closer together. By watching the timing of the pulses, astronomers have seen this dance unfold. The stars spiral inward as predicted, their pulses arriving sooner and sooner, confirming that gravity behaves as Einstein described. Long before detectors on Earth measured gravitational waves directly, pulsars had already proved their existence. The pulsar thus becomes more than a clock. It becomes a laboratory for physics at extremes. Within its pulses, we test theories of gravity. We measure the density of matter. We probe the structure of space-time. No laboratory on Earth can match such conditions. No machine can reproduce the pressure of a neutron star. But in the pulses, we find a substitute. They are signals broadcast across light years, carrying the imprint of collapsed matter and warped space. And yet, the pulses are not cold numbers. They are also beacons, sweeping through the night with a rhythm that feels almost alive. Imagine standing on a planet that lies within the path of a pulsar's beam. Every second, a flash of radiation would wash across the sky, a lighthouse that turns with unwavering certainty. For millions of years, that pulse would repeat, steady as a heartbeat, marking the passage of time in a cosmos where stars are born and die. It is a signal not intended for us, not meant to be seen, yet it reaches us across the gulf of space. The discovery of pulsars in the 1960s was at first a mystery. The signals were so regular, so unlike any known cosmic source, that the astronomers who found them wondered if they might be artificial. They called them LGM, for little green men, as a joke born from genuine astonishment. But as more pulsars were discovered, scattered across the sky, the truth became clear. These were not messages from another intelligence. They were the voices of dead stars, the echoes of collapse, the rhythm of gravity itself. The regularity of pulsars is not a coincidence. It is a consequence of their density, their gravity, their stability. The same forces that crush a sun into a city, that make a teaspoon weigh billions of tons, also make the star spin with unstoppable steadiness. It is the unity of extremes. Destruction gives rise to order. Collapse gives rise to rhythm. Density gives rise to signal. Pulsars are the proof that the universe can turn chaos into clarity, violence into precision, collapse into light. The pulses that reach us across the abyss of space are not only remarkable in their precision, they are also remarkable in what they reveal. Each tick, each beam of radiation sweeping past Earth, is a direct consequence of the density that gives the famous teaspoon its weight. Without that density, the neutron star could not spin so rapidly, could not sustain its magnetic fields, could not shine with such steadiness. The teaspoon fact and the pulsar signal are not separate curiosities. They are threads of the same fabric, woven together by collapse. Think of the teaspoon once more. Its billions of tons in a spoonful seem absurd until we see what that density does to a star's rotation. The collapse that compresses matter also spins the core faster, and the matter pressed into neutrons provides the stability for that rotation to continue for millions of years. The teaspoon's weight becomes the pulsar's heartbeat. The crushing gravity that gives mass its meaning becomes the mechanism that allows beams of light to flash in perfect rhythm. Every pulse we observe is proof that density holds. Every pulse is the teaspoon speaking across the gulf of space. The unity between the metaphor and the measurement is striking. On one side, the teaspoon is the way we explain neutron stars to ourselves, turning incomprehensible density into a household image. On the other, pulsars are the way neutron stars explain themselves to us, turning collapse into signal, broadcasting the truth of their existence. The teaspoon is our story, the pulsar is theirs. Together they bridge imagination and observation, making neutron stars not just objects of theory, but beacons of fact. Astronomers use these pulses to test the laws of physics, to probe the behavior of matter and space-time under extreme conditions. Each pulse arrives with a timestamp written by nature, more precise than anything our laboratories can produce. In binary systems, where two neutron stars orbit one another, the pulses reveal the shrinking orbits caused by gravitational waves. In solitary pulsars, the pulses reveal the slowing spin, the loss of energy as the star radiates into space. In every case, the signals are rooted in the same density that makes the teaspoon weigh so much. Thus, when we marvel at the famous fact, we are not only indulging in curiosity, we are touching the very reason neutron stars can be studied at all. The teaspoon fact is not a sideshow. It is the essence of pulsars, the reason they shine, the reason they endure, the reason their beams sweep through the darkness. Without density, there would be no pulses. Without pulses, we would never know the weight of a spoonful. The chapter closes with this thought. The teaspoon and the pulsar are two expressions of the same truth, that matter, when crushed to its limits, creates both unimaginable weight and unimaginable order. Collapse gives rise to catastrophe, but also to stability, to rhythm, to light. The teaspoon teaches us density, the pulsar teaches us time, and together they prepare us for the next frontier, where neutron stars meet their final rival. For if a neutron star becomes too massive, even neutron degeneracy fails, and collapse continues without end. The next step in our journey is to place the teaspoon beside the black hole, to see what happens when matter falls beyond even light's escape. The neutron star is the last bastion of matter before gravity claims victory. It is the final stage where the forces of physics still resist, where neutrons pressed shoulder to shoulder provide a pressure strong enough to hold back collapse. But the balance is delicate, and it exists only within a narrow window. If a star's remnant is too light, it will stop at a white dwarf, supported by electron pressure. If it is heavy enough, it will collapse to a neutron star, stabilized by neutron pressure. But if it grows heavier still, if its mass passes a critical threshold, even neutrons cannot endure. The teaspoon that once carried billions of tons becomes meaningless, for the star itself vanishes into a black hole. This threshold is called the Tolman-Oppenheimer-Volkoff limit, the maximum mass that neutron degeneracy can support. The exact value is uncertain, but astronomers believe it lies between 2 and 3 times the mass of the Sunday. Beyond this, no known force can stop gravity's inward pull. The neutrons themselves dissolve, the star's structure crumbles, and space-time folds inward to create an event horizon. The neutron star is the last visible object before that abyss, the final stage of matter, before it disappears into invisibility. To compare neutron stars and black holes is to compare the last stand of matter with the victory of gravity. The neutron star is a city-sized object weighing as much as the sun, its surface gravity crushing yet finite, its pulses still shining into space. The black hole is not an object in the same sense. It is a region from which nothing escapes. Not light, not matter, not signal. The neutron star bends light, but the black hole captures it. The neutron star slows time near its surface, but the black hole freezes it at its horizon. The teaspoon of neutron matter weighs billions of tons, but inside a black hole, the concept of a teaspoon vanishes. There is no density we can measure, no surface we can touch, and yet, the two are bound together, for one often becomes the other. Binary systems of neutron stars can collide, their masses merging to form a remnant too heavy to survive. In those collisions, gravitational waves ripple outward, shaking space-time itself, while the final object collapses into a black hole. Astronomers have seen these events through detectors that listen to the tremors of gravity, and in them, we witness the transition from density to disappearance, from pulsar to abyss. The comparison also deepens our sense of scale. The neutron star astonishes us with its density, with its teaspoon that outweighs mountains. But the black hole makes even that comparison seem modest. For the black hole, there is no spoon, there is only the horizon, the point of no return, the edge beyond which the language of weight and density dissolves. The neutron star is the last place where matter still holds meaning. Beyond it, we cannot speak of matter at all. And so, when we hold the teaspoon in imagination, we are also holding the limit of what can be described. The teaspoon belongs to the neutron star, but it cannot belong to the black hole. The comparison ends where matter ends. The teaspoon teaches us density, but the black hole teaches us silence. To pass from one to the other is to pass from the measurable to the unknowable, from the visible to the hidden, from the crushing of atoms to the collapse of space-time itself. The neutron star and the black hole stand side by side in imagination as two different answers to the same question. How far can gravity go? The neutron star shows us the last surface, the last resistance, the last place where matter still holds form. The black hole shows us what happens when even that resistance fails. Here, comparison is not simply weight against weight, but visibility against invisibility, density against collapse, light against silence. Imagine standing on the surface of a neutron star. The gravity is billions of times stronger than Earth's, crushing yet finite. Light struggles to escape, bending and reddening, but it does escape. Signals beam across the cosmos, pulses arrive with clock-like precision. Radiation bursts into space. The neutron star still has a surface, a boundary we can describe, an object we can measure. Its teaspoon still carries meaning, for density still exists. Now imagine approaching the event horizon of a black hole. There is no surface, only a boundary beyond which nothing returns. Light that tries to escape fails, pulled back into the abyss. Time itself slows as you near, stretching seconds into eternities. To an outside observer, you freeze at the horizon, never crossing, never returning. To you, the fall continues, unstoppable, unmeasured, unseen. Here the teaspoon vanishes as an idea, because there is no density to weigh, no matter to describe. There is only curvature of space-time, collapse without end. The difference between these two fates lies in mass. A remnant of 2 suns may stabilize as a neutron star, but a remnant of 3 suns will collapse into a black hole. The line is narrow, the margin thin, yet the outcomes are worlds apart. One gives us pulses, signals, matter, compressed, but present. The other gives us silence, absence, the disappearance of matter into geometry. The neutron star is the last place where we can ask about teaspoons. The black hole is where the question dissolves, and yet the two are connected. Neutron stars can merge, spiraling together in dances that send gravitational waves across the universe. When they collide, they can form black holes, their combined mass breaking the limit that neutrons can resist. In those final moments, we see both worlds at once. The density of neutron stars, the light of their collisions, the birth of a black hole where no light remains. The teaspoon and the horizon are linked in a chain of collapse, one leading inexorably to the other. The comparison is humbling. The neutron star astonishes us with density, with gravity, with pulses across space. But the black hole shows us what lies beyond astonishment. It shows us the edge of knowledge, the place where language falters, where even physics becomes uncertain. The neutron star gives us numbers, weights, and measures. The black hole gives us questions, silence, and mystery. The teaspoon belongs to one, but not the other. The neutron star is the cliff's edge of matter, the last step before gravity swallows everything. To see this clearly, let us hold the teaspoon in thought one final time. It is heavy beyond imagination, billions of tons compressed into the hollow of a spoon. But it is still something we can describe. It is still matter. It is still a form of existence that can be weighed, measured, and compared. This is what makes neutron stars so extraordinary. They are the end of matter as we know it, but not the end of matter itself. Beyond them lies the black hole, where the teaspoon ceases to have meaning. Inside the horizon, there is no density we can calculate, no surface we can touch, no object we can hold. Matter collapses past visibility, past resistance, past all description. Where the neutron star shows us the power of physics, the black hole shows us its silence. The teaspoon fact, so vivid and astonishing, belongs entirely to the neutron star. The moment collapse goes further, the image dissolves into darkness. This boundary between neutron stars and black holes is one of the most dramatic in the universe. On one side, we can study pulses, measure masses, trace gravitational fields, and imagine teaspoons. On the other side, we can only calculate horizons, infer effects, and wonder about what happens beyond sight. Neutron stars are laboratories we can observe, their densities extreme, yet still part of the world of measurement. Black holes are mysteries we can only approach indirectly, their very existence confirmed not by light, but by its absence, not by surfaces, but by shadows. And yet the existence of neutron stars tells us something vital about black holes. It shows us where matter fails, where physics bends, where collapse continues unchecked. Every teaspoon of neutron star matter, every pulse of a pulsar, every gravitational wave from merging binaries is a signpost pointing toward the abyss. The neutron star is the last stand of resistance before gravity erases matter. It is the final page of the book of density before the story turns into silence. To compare them is to feel the scale of the cosmos. The neutron star weighs suns in the size of cities, bends light and time, and sends beams across the universe. The black hole swallows suns without trace, bends light into oblivion, and seals time behind its horizon. The teaspoon captures the wonder of the one, but cannot touch the mystery of the other. Between them lies the thin boundary where physics gives way to gravity, where our metaphors collapse as surely as matter itself. And so the chapter closes. The neutron star is the last visible frontier before the black hole, the last stop where weight and density still exist. The teaspoon is not only a fact but a symbol of this threshold, proof that the universe can compress mountains into spoons and stars into cities, but also a reminder that beyond the spoon lies a silence deeper than imagination. From here, we turn not into the abyss, but back into the neutron star itself, to ask what it teaches us about matter, about particles, about the fundamental forces of nature pressed to their limits. A neutron star is more than a remnant of collapse. It is a message written in density, a laboratory forged by gravity, a natural experiment that cannot be repeated anywhere else in the universe. When we imagine the teaspoon, we begin with weight, but the true lesson lies deeper. That impossible heaviness is the doorway into questions of physics that challenge our understanding of matter itself. What happens when particles are pressed so close that the space between them vanishes? What forces emerge when matter is stripped of its familiar structure? What new states of being reveal themselves under pressures beyond anything on Earth? On our planet, the densest matter we can create is still trivial compared to a neutron star. Diamond, the hardest natural substance, is nothing more than carbon atoms arranged in a rigid lattice. Yet, it is mostly empty space. In particle accelerators, we smash nuclei together to glimpse fragments of extreme density. But these collisions last only instants, and the droplets created are too fleeting to study in detail. Neutron stars do not last instants. They endure for millions, even billions of years, holding their matter steady under forces that erase chemistry and transform atoms into something entirely new. The surface layers already defy our imagination. Here, nuclei are packed together into strange shapes scientists call nuclear pasta, patterns that resemble sheets, rods, or labyrinths of matter compressed into unfamiliar geometries. These formations arise from the competition between nuclear forces pulling particles together and electrical forces trying to push them apart. No such structures exist on Earth, but in the outer crust of a neutron star, they may dominate, forming textures more complex than any crystal we know. Beneath the crust lies the ocean of neutrons, the substance that gives the teaspoon its impossible weight. In this ocean, neutrons behave like a quantum fluid, a state where particles flow without resistance, a superfluid that could climb walls and whirl in vortices. Alongside it may exist superconducting protons, carrying currents without loss, creating magnetic fields of inconceivable strength. A neutron star is therefore not only dense, but also exotic. It is a place where the fundamental rules of quantum mechanics shape matter on scales measured in kilometers. And deeper still, at the very core, lies mystery. Some theories suggest that neutrons may break apart into their constituent quarks, creating quark matter, a soup of the most elementary particles known. Others imagine even stranger states, hyperons, with exotic quark combination, or condensates of mesons, forming new phases of matter. No telescope can peer inside to confirm which is real. The heart of a neutron star is hidden, revealed only through indirect clues. The star's mass, its radius, its cooling rate, its collisions with companions. Every observation is a clue to the puzzle, but the final answer remains beyond our reach. This is the lesson the teaspoon teaches. Its weight tells us that matter can be pushed into regimes where our theories strain, where even the strongest forces of physics must be reconsidered. Neutron star matter is not a simple curiosity. It is a window into the limits of nature, a challenge to our understanding of the strong nuclear force, of quantum fluids, of matter at pressures so great that even protons and neutrons may dissolve. When we think of neutron stars, we often begin with awe. We picture the teaspoon that outweighs mountains, the surface gravity that crushes time and light, the pulses sweeping across the cosmos. But behind that awe lies knowledge waiting to be uncovered. Each neutron star is a laboratory, older and greater than any we could build. Each teaspoon a symbol of questions that drive our science forward. They remind us that collapse is not only an end but also a beginning, that in the death of stars lies the chance to learn the deepest truths of matter. The deeper we travel into imagination, the stranger the states of matter become. The ocean of neutrons alone defies all intuition, but the core of a neutron star may conceal still more exotic forms. Under pressures so immense that even neutrons may lose their identity, quarks, the fundamental constituents inside protons and neutrons, could be freed from confinement. If so, the heart of a neutron star may not be made of neutrons at all, but of quark matter, a dense soup where up and down quarks float freely, perhaps joined by heavier, strange quarks. In this state, the particles that normally hide inside nuclei become a continuous fluid, a form of matter unknown on Earth, except in fleeting moments inside particle accelerators. To imagine quark matter, think of breaking apart every neutron in a teaspoon of neutron star material and allowing the quarks to roam without bonds. Instead of billions of tons of neutrons pressed together, you now have an even denser soup of quarks, flowing and shifting under forces we can only calculate in theory. Some physicists suspect that such matter could be stable, that strange quark stars might exist, composed entirely of this exotic fluid. If so, the universe may hold objects even denser than neutron stars, stars where the teaspoon would weigh even more, stars where the crushing of matter has gone beyond neutrons themselves. But we cannot see directly into these cores, and so we turn to experiments on Earth. In vast machines such as the Large Hadron Collider, physicists smash heavy nuclei together at nearly the speed of light, recreating for an instant the densities and temperatures that may exist in neutron stars. For less than a trillionth of a second, The collisions create droplets of quark-gluon plasma, the very state thought to have filled the universe just after the Big Bang. These droplets are too short-lived to study directly, but the particles they release offer hints of how quarks behave when freed. In this way, Earth laboratories become miniature echoes of neutron stars, glimpses into the conditions that sculpt their cores. Even with such experiments, uncertainty remains. The equations of the strong nuclear force, the fundamental theory governing quarks and gluons, are fiendishly complex. They resist easy solutions, leaving scientists with models and approximations rather than certainties. Neutron stars therefore serve as the ultimate test. By measuring their masses and radii, by studying how they cool, by observing the gravitational waves from their collisions, astronomers can constrain the physics of their interiors. Every observation is a data point, narrowing the range of possibilities, guiding us toward the truth of what matter becomes when crushed to extremes. The lesson here is that neutron star matter is not just dense, it is instructive. It is a natural experiment in quantum chromodynamics, the theory of the strong force. It shows us what happens when the most fundamental particles are pressed together by gravity, stronger than anything else in the cosmos. And though we may never scoop a teaspoon from their surface, we can still listen to their pulses, measure their masses, and watch their collisions to uncover the secrets within. The teaspoon, then, is not only a metaphor for weight, it is also a metaphor for knowledge. It reminds us that the universe itself is the greatest laboratory, running experiments we cannot reproduce, offering us results we can observe, but not control. Each teaspoon of neutron star matter is a textbook written in density, a page in the story of matter under pressure. To read it, we must look across light years, interpret signals, and trust the language of physics. The answers it holds are not only about stars, they are about the fundamental nature of reality itself. The neutron star stands as a bridge between the vastness of the cosmos and the smallest scales of matter. It is created by the collapse of something as immense as a sun, yet its secrets lie in the behavior of quarks and gluons, particles smaller than imagination. In this union of the very large and the very small, we find the essence of modern physics. To understand the teaspoon of neutron star matter is to see how the crushing weight of gravity can transform the rules of the atomic nucleus, forcing particles into states that no laboratory can sustain for more than an instant. This is why neutron stars fascinate both astronomers and particle physicists. For astronomers, they are cosmic objects, lighthouses, and remnants, measuring tools for space-time. For particle physicists, they are laboratories of the strong nuclear force, places where the interactions of quarks and gluons shape entire stars. The line between the two sciences dissolves here, because a teaspoon of neutron star matter cannot be explained by astronomy alone, nor by particle physics alone. It requires both the mathematics of general relativity to describe the gravity and the mathematics of quantum chromodynamics to describe the particles. In this sense, every observation of a neutron star is a chance to test the deepest theories. When gravitational wave detectors catch the tremors of two neutron stars colliding, they are not just recording cosmic violence. They are probing the stiffness of nuclear matter, the way neutrons resist compression, the possibility of quark matter emerging in the core. When X-ray telescopes measure the radius of a neutron star, they are not just mapping a distant remnant, they are setting limits on the forces that hold the nucleus of every atom together. The teaspoon is not just heavy, it is revealing. Even the cooling of a neutron star becomes a lesson. As they radiate heat over millions of years, their temperatures fall in ways that depend on the particles within. End. If exotic particles like neutrinos stream freely through their cores, the star cools more quickly. If superfluids and superconductors dominate, cooling slows. By measuring the temperatures of these distant remnants, astronomers can infer the physics of particles that exist nowhere else. In this way, The teaspoon becomes a thermometer, its weight, a clue, its glow, a message. The true power of the teaspoon metaphor is that it makes the incomprehensible tangible. It allows us to imagine holding in our hand the weight of a mountain, the mass of humanity, the density of collapsed suns. But its deeper power lies in what it represents: the bridge between human imagination and cosmic truth, between the stars above and the particles within. The teaspoon is not merely a curiosity to impress. It is a symbol of the unity of physics, a reminder that the universe is one, that the same forces shaping quarks shape galaxies, that the same collapse that ends a star teaches us the fundamentals of matter. And so, as we place the teaspoon back into thought, we see it not as an end, but as a beginning. It is the opening line of a conversation between humanity and the cosmos, a symbol of the questions that drive us to build telescopes, to construct colliders, to listen to the pulses of dead stars across light years. It is weight made metaphor, density made story, collapse made knowledge. The teaspoon shows us that the universe does not simply destroy, it also teaches. It compresses, it reshapes, it challenges us to learn. The chapter closes with this realization: a teaspoon of neutron star matter is not only heavy, it is meaningful. It is a window into the limits of matter, a bridge between the macroscopic and the microscopic, a symbol of how collapse can teach creation. From here we step toward wonder itself. For the final lesson is not only physics but perspective. The teaspoon is not just science, it is awe. The journey began with collapse, with stars burning their last fuel and falling into themselves. We watched as fusion faltered, as gravity tightened its grip, as supernovae blasted layers into the void, and left behind cores that defied comprehension. We held a teaspoon of their remnants in thought and felt its impossible weight. 1 billion tons pressed into something we could almost imagine resting in our palm. We followed that teaspoon through comparisons to Earth, to mountains, to humanity itself, until the numbers blurred into awe. And now, at the end of this path, the lesson is not only about density, it is about wonder. A neutron star is an object of science, described by equations and confirmed by observation. Yet it is also a symbol, a reminder that the universe creates realities far beyond our everyday scale. It tells us that matter can be crushed until the spaces between particles vanish, that gravity can bend light and time into new forms, that collapse can create order rather than chaos. The teaspoon is a bridge between the ordinary and the extraordinary, a metaphor that makes the incomprehensible just close enough to touch. This weight of wonder does not lie only in numbers, it lies in perspective. When we hold the teaspoon in imagination, we are reminded that our world, our bodies, our entire planet are made of matter that is mostly empty space. We are reminded that the stars above us are fragile, burning their fuel for only millions or billions of years before collapse. We are reminded that the universe holds scales of force, density, and time that stretch our minds to their limits. The teaspoon of neutron star matter is not only heavy, it is humbling. It humbles us by showing how small we are. It humbles us by showing how vast the cosmos island, and it humbles us by revealing that the laws of physics, which govern our simplest machines and our everyday lives, also govern the most extreme objects in the universe. The teaspoon weighs 1 billion tons not because of magic, but because of the same principles that let an apple fall from a tree, the same gravity that keeps us on Earth, the same nuclear forces that light our sun. The difference is scale. The wonder is that the same rules can create such extremes. The story of neutron stars is also the story of imagination. Without imagination, the teaspoon is just a number, an absurd claim. With imagination, it becomes a portal to understanding density, gravity, quantum mechanics, and relativity. It becomes a way to see how collapse creates beacons, how pulses sweep across space, how matter resists and then yields. Science and imagination meet in the teaspoon, each strengthening the other, each turning data into meaning. And so the book closes with a single image, A teaspoon, small, ordinary, held in the hand, but filled with the matter of a neutron star. It outweighs mountains, nations, and humanity itself. It is proof that the universe can compress suns into cities, cities into spoons, and spoons into metaphors. It is proof that reality is greater than imagination, that wonder is not fantasy but fact. The teaspoon of neutron star matter is heavy with more than weight. It is heavy with knowledge, with humility, with awe. In that weight we find not only science but perspective. We find not only density but meaning, and we leave with this final truth. A teaspoon of neutron star weighs 1 billion tons, and with it weighs the wonder of the universe itself. The teaspoon rests in imagination, shining as a symbol of what the universe can do with matter. But to complete this vision, we must step back and see the larger picture. The universe does not create neutron stars in isolation. They are part of the grand story of stars, born from the same hydrogen clouds that once gave rise to our own Sunday. They are the end chapters of stellar lives, the remnants of fire turned into silence, the monuments left behind by fusion's death. In them, we see both the fragility and the resilience of the cosmos. Consider the contrast between our world and the neutron star. Earth is gentle, shaped by oceans, winds, and the patient motion of continents. Our gravity holds us softly, allowing plants to grow, rivers to flow, and creatures to rise from the sea. We weigh ourselves in kilograms and pounds. We measure distances in meters and miles. We live within scales that feel absolute. And yet, in comparison to the teaspoon of a neutron star, all of Earth's mountains, valleys, and oceans shrink into insignificance. The teaspoon becomes a mirror in which we see our smallness, but also our connection. For the atoms in our bodies are the same atoms that once burned in stars, the same particles that, under different fates, could have been pressed into that impossible density. This is the poetry of science, that we are made of stardust, that the iron in our blood and the calcium in our bones were forged in stars, that the collapse which creates neutron stars is the same process that enriches the universe with the elements of life. A neutron star is not only an object of physics, but a relative, a cousin in the family of stars, a reminder that we too are part of cosmic cycles. The teaspoon is not only heavy with matter, it is heavy with meaning, with the story of creation written into collapse. And yet, the wonder is not meant to overwhelm us with despair. It is meant to remind us that the universe is richer than our imaginations, that reality itself can surpass the wildest visions of fiction. The teaspoon of neutron star matter is not an end point, but a starting point. It is the spark that makes us ask questions, build telescopes, construct particle colliders, and dream of futures where we may probe the cosmos even further. In that sense, the teaspoon is both a weight and a key, both a burden and a gift. It teaches us humility, but also curiosity. It shows us that we are small, but also that we are capable of understanding the very forces that shape the universe. That is the true weight of wonder, not only the crushing density of matter, but the uplifting power of knowledge. The journey ends where it began, with a single teaspoon. At first, it was a curiosity, a fact repeated with disbelief, a claim that something so small could outweigh mountains and nations. But as we have followed its path, the teaspoon has unfolded into something far greater. It has carried us through the life of stars, through the violence of supernovae, through the crushing of atoms, through the birth of neutron stars, through the sweep of pulsar beams, and through the final boundary where black holes claim the last word. It has shown us that density is not an abstract number, but a force that bends light, reshapes time, and challenges the limits of matter itself. The teaspoon has become a guide to physics at its most extreme. It has revealed the power of degeneracy pressures, the strength of nuclear forces, the possibility of quark matter and exotic states hidden in stellar cores. It has linked the very small with the very large, showing that the behavior of quarks inside a nucleus can decide the fate of suns. It has become a bridge between particle physics and astrophysics, between laboratory and cosmos, between imagination and reality. But beyond science, the teaspoon has become a mirror. In its impossible weight, we see our own smallness. In its crushing density, we see the fragility of ordinary matter. And in its endurance, we see the resilience of the universe. The way collapse can give rise not only to silence, but also to signal, to pulses that sweep across the cosmos and mark time with a steadiness beyond any clock we can build. The teaspoon has carried us not only into physics, but into perspective. The final truth is that a teaspoon of neutron star matter weighs 1 billion tons. That is the fact, but the meaning is larger. It tells us that reality is capable of wonders beyond imagination, that the same laws of physics which let us stand on Earth also sculpt stars into cities, mountains into spoons, time into rhythms of light. It tells us that the universe is not merely vast, but profound, filled with truths that humble and inspire in equal measure. So the image remains: a teaspoon, ordinary and small, held in the hand, but filled with the matter of a neutron star. It outweighs worlds. It is the weight of mountains, of nations, of humanity itself. It is the weight of wonder, compressed into something that fits between fingers. And in that image, we carry forward both knowledge and awe, both science and story, both humility and hope. The universe is heavy with meaning, and in a single teaspoon, it has given us proof.